Hello, my name is Warren, and I'm going to be presenting my Math 410 midterm project, where we're analyzing the bias variance trade-off. I'm just going to be going through my Jupyter notebook and explaining it as I go along. So we first start off by importing the relevant packages and defining our ground truth model, which is given by this f of x equation right here. Now we'll generate observations for our training set. We're going to generate 1,000,000 observations. These are in the form of xy coordinates, where the x is in the interval -2 and 2, and the y is found using this generative model, where y is equal to the ground truth model plus some noise, which is this epsilon here. And this epsilon is it's a Gaussian distribution with mean 0 and standard deviation 1. So next, we're going to generate observations for our test set. Now this is 100,000 observations. Likewise, it's uniformly distributed in the interval between -2 and 2, and using the same generative model of above. Where we take the ground truth model, this time evaluated at one of the x test values, and add some noise to that. So visualizing this, you can see from the plot that our red line is our ground truth model, and the blue observations are our 1,000,000 training set observations that we found, whereas the orange dots are our test observations, the 100,000 test observations that we found. So next, we're going to, where is it? There it is. Next, we're going to fit this model, and this is given to us in the directions, and note that this d is the degree of the polynomial, and we're going to be fitting this model using a degree 5 and a degree 20 polynomial. We'll get more into that in the next section. So moving forward, to train the model, we're going to use sample sizes of 200, 500, 1,000, 2,000, 5,000, and 10,000. And for each of these sample sizes, we're going to perform 100 experiments. And in these experiments, we're going to sample data points from the original 1,000,000 set of training data points, training data values. And we're going to use these to fit the model. So for example, if we are training the model with a sample size of 200, that means we're going to select 200 data points randomly from that 1,000,000 training set and use those to fit our model, and then we can make predictions and test the error and whatnot. So to train the model, we can use a simple nested for loop, which does what I just described. It randomly selects however large our sample sizes, it selects that many data points from our training set and uses those to train the model. And then we can calculate the squared train error as well as the y hat test, which is our predictions with the model. So for each experiment, we're going to estimate the average squared training error, which we did above, the average squared test error, the squared irreducible error, and the variance in our predictions. So jumping forward to the visualization, here is the model with a polynomial of degree 5. And we can see right off the bat that our test and training error are both very high, our bias is very high, and our variance is very low. So this would suggest that our model is underfit since we're seeing such high values for our test and train error. Additionally, you can see this orange line right here shows that the test and the training error both converge to the bias squared plus the error. So moving forward, now we're going to train our model on a degree 20 polynomial. Since I already went through the instructions and the process for the degree 5, the degree 20 is the same process essentially. So I'm just going to skip ahead to the visualization. Now we can see a much different image here, where notice that the test error and the training error are much lower. And initially we start out with high variance and low bias. Once again, our test and train error converged to this orange line, which is the bias squared plus the error. So we can verify that that is indeed true. All right, so looking at both of these together, we can see that the test error converges, the training error and the test error converge much quicker for this model of degree 5 polynomial, whereas it takes a lot longer for the degree 20 polynomial. Additionally, we can see, as I pointed out before, that there's much higher error in degree 5 polynomial than in the model with the degree 20 polynomial. And so the model 20 polynomial is a much better fit for this data. So that's all I have for you guys today. Thank you for tuning in, and I'll see you in class.